And we are looking forward for the actions and participate in it with lots of colleagues are interested in. And now I think after the AI, I would like to ask Sofia from the CERN Technology Initiative that you can tell us about the other side, that how quantum technology is working. And I think our basic expectation that very, very soon, maybe even much sooner, the quantum technology and the artificial intelligence will be bind together. And now that will be extreme. I cannot imagine what will happen in that case. So once more, let us thank you. Thank you. And Sofia Vallecorsa,
yes.
You have, how much is the time?
No, it's 10, yes.
Yeah, perfect time. You have 40 minutes plus questions and answers.
Thank you. Okay, so 40 minutes seems like a very long time. By experience, I know I typically run late. So please let me know if that's happening because I can stop. Thank you. So this is what I will talk to you about. The Quantum Technology Initiative, the way it started, its main goals, how it evolved, and now we turn in our second phase. We're very proud to say that we started in January 2024. And the first thing I want to say, and this connects to my questions before, so I don't need to explain to you what we do at CERN. Very important fraction of the CERN scientific program wouldn't be possible without the Hungarian contribution. But I kept this slide here because I want to stress at the very beginning of my talk, I'm here to talk about quantum, but quantum is not CERN core business, okay? CERN is a physics lab. We are interested in physics. We are interested in experimental physics at colliders and beyond. This really gives the flavor of what the Quantum Technology Initiative is. And that's why I very much relate to the discussion we just had about the fact that research needs to start as a research in some fields, especially those tools like quantum computing, like AI, has to start at a very practical level, has to be very tight connections to the applications. So in particular, if I had to try and summarize why CERN is engaging in quantum technologies, you can think of it of the two aspects. And the first is what I just said. Can we actually okay, sorry. Can we actually use quantum technologies to do better physics? What is the impact of technologies such as quantum computing, quantum communications, sensing for the future of research? How does it integrate in the general CERN research program? But there is also another aspect. There are a lot of interesting technologies that we have to develop because of the work we do with physics, because of our detectors, because of the theory models that we develop. And so is there anything among those that we can actually reuse to do it, to help improving quantum technology, to help driving them towards a better, or let's say a more applicable formulation, okay? So this is something that is very, very important, I think, for CERN. And I will hope to be, I will give you a few examples of this. So how did it all started? It actually started earlier than 2020. That's the date that the initiative was officially launched. But a couple of years before that, maybe some of you might remember, if you were at CERN, we had organized a very, initially low-profile workshop and tried to understand what was the interest of the community on quantum computers, on quantum computing in general. So we invited a lot of external speakers. And by the time we got closer to the date, we realized that we had more than 300 people registered, and the main auditorium at CERN, the day of the workshop, got completely filled up. So we realized that actually the interest was huge, and nobody had ever talked about this or thought about this before. So that's how we started working on launching this initiative. I must say I was there from the very beginning, but at that time, as I said, someone before, I was really working on the computing side. And you can see here the main objectives here. And the idea really of, again, trying to find out those sweet spots where CERN could contribute actively to the development of quantum technologies, trying to evaluate the impact of those technologies for CERN, again, priorities to our physics program, but also, and this is very, very important, how do we align with other existing institutes? I didn't report here a map of how those quantum initiatives are distributed across the globe. But if I did, you would see spots everywhere. and very, very large spots even, okay? So the investments and the amount of funding that's dedicated to these technologies is huge for different reasons. So it is important that CERN aligns its own work to the initiatives that are ongoing, in particular in the member states, but also in all of the other, I would say, geographical realizations of our high energy physics community. And because of that, the way this initiative was shaped was really at the level of an exploration. We wanted it to be as broad as possible, a kind of, exploration of the largest possible landscape. And so the initiative was organized in 4 main areas: applications to simulations, in particular applications to, applications that could be useful for our theoreticians, quantum computing, so the development of quantum algorithms and the use of quantum computers for our problems, so not the development of hardware. This is not something that's happening at CERN. But what's happening is the development of new sensors, or at least the studies of the possibility of using quantum effects to build better detectors in the future, and also, in just 3 years of life, of it in its own, life, this initiative actually produced a huge amount of scientific results. And I want to stress, and this I can tell you as a fact, because I was responsible for the computing area, that at least in the computing area, 99% of the work was done by PhD students. So we were very, very happy about that, because the contribution, we managed to do relevant scientific contribution with a very young workforce, okay? So I think this is something that shouldn't be neglected. Some results. I have backup slides with a lot of references. I guess you can go through them later on. I just wanted to highlight the themes here. So as far as theory and simulations is concerned, there were a lot of applications that were surveyed across all of the problems that if there are theoreticians among you, probably know this better than me. My background is experimental, okay, physics, so I guess it shows in the way I talk. So applications to lattice QCD calculation to speed up simulations. The idea of modeling behavior of quantum sensors in order to their sensitivities to the different physics program, like gravitational waves and dark matter searches. The study of atomic clocks that could be used in the context of our detectors. For example, what we're doing now at the antimatter factories at CERN. Then anything that has to do with computing, and you will see that I will mostly talk about this, it's closer to your heart. So if you know how data processing works for big experiments, you can recognize there all of the different steps that are typical of these data processing chains. And basically for each one of those algorithms to really evaluate what is it that we could actually do, or let's say that we can do with this technology at this time. And it turns out there are actually quite a lot of things that you can do. Discussion on whether it's more or less efficient than using a cluster of GPU is still open. But I think it's important to stress that this is possible, and it's coming. And of course, we also had a role that was closer to to the facilitator role. We need to take care of how to set up infrastructure that would allow our researchers to actually do this kind of project. Sensing, metrology, and materials. I already said something about this. In particular, the experiments that at CERN. So CERN is not just about collider physics. We have quite a few experiments that are looking for very precision measurement and for very small, low probability processes, searches for dark matters, for example. And those kind of experiments are very much interested in looking into new sensing technologies for the detectors, especially calorimeter. So measurement of small amounts of energies. And then there is the part about communication and network. During QTI-1, this part was relatively small in the sense that when people think about quantum communication, they think mostly about cryptography and the possibility of secure transfer of data, secure data transfer. And this is not necessarily, or was not up until now, for CERN a priority, naturally. Because even if a hacker got hold of our data, they wouldn't know what to do with it, obviously. But that's changing now. You will see that for phase 2, we are actually pushing a lot more into understanding, not that much from the point of view of secure data transfer, not yet, but really towards building the future of internet, okay? Quantum distributed systems for computing. Distributed quantum systems for computing. So. But since I was talking about communication, I'll get it out of the way right away, in the sense that we only had a major project on quantum communication, and it's what's called a quantumacy. So I decided to show it to you now. What I really like about this project, this was done in collaboration with IDQ, which is a secure quantum key distribution company. Well, it's multinational, but they have headquarters in Geneva. And it was also part of the European Open QKD network. And what I really liked about this is the fact that this was a practical implementation of federated learning implementation. So distributed AI-based analysis of medical data that we demonstrated we could do across the network secured through quantum key distribution. Okay, so in particular, our CERN own contribution to this project was the a simulator we set up that was really comprehensive. We were actually, we took care of also implementing possible attacks that could happen on the network, but also all of the AI-based analysis of the data was actually done at CERN. And this is what I should have, the slides I should have showed you. Sorry, apologies about that. So, well, in addition to what I just said, is the stress that this was an analysis of medical imaging, so MRIs and X-rays images. The part about homomorphic encryption is mentioned is, so the nice thing about homomorphic encryptions, if you want, is that it's the ultimate security for me. It's the ultimate security approach, because through homomorphic encryption, you do not need to decrypt your data if you want to analyze it. And used in conjunction with machine learning, this can be a very powerful tool. Okay, so that was an aspect that was also within the scope of this project, but honestly, most of the work we did was really based on the quantum key distribution part, not so much on the development of new AI tools that could be compliant with homomorphic encryption. We can discuss more about this if you're interested. Now, if I go more specifically about talk about computing, this is probably not another picture that you need to see, because you know this very, very well, but CERN people do like to say that we are producers of big data. But in fact, we are not analyzers of big data. Because if you look, so this is LHC raw data in 2018, and you can see how it compares to other major players in the big data landscape. But this is without trigger selection. This is the data that in 2018, our accelerator, the LHC, was producing. This is not what we actually analyze, okay? Because most of the data is thrown away. We just analyze a very, very small percentage. What you had here in the big data center, what you helped CERN in analyzing and, to get out all these nice physics results is actually a tiny fraction of all of that. And I want to stress this because it's another important point. If we could get to the point to which we could actually analyze most of what's produced, then I think the reach, the scientific reach, the potential of new discovery would very much increase. And again, you probably don't need to see this. You know these kind of pictures very well, and Alice actually has much busier pictures than those, probably. This is the major computing challenge that the LHC has for the future. Okay, so a large amount of data, high dimensional data. Okay, so now the question is, if this is our major challenge, is quantum computing the best tool to actually try and address this? It's not clear at all, because at the moment, quantum computers are not good at dealing with this kind of data. It's too big, it's too many features, too many aspects that need to be analyzed at the same time, okay? So is it this, though, temporary, a limitation that exists today, or is it something, and it will be overcome with the next generation computers, or is it something that will stay, so that it's fundamental in the way quantum computers work? You see that the question is really, really important. So I'll give you an example of of an algorithm that is actually working, and it goes in that direction. And it's an algorithm that could, in principle, run at the trigger level in order to improve, the analysis of that gray ball that I showed you at the beginning. And it starts with a motivation that, again, it's kind of controversial. I don't know many physicists, like experimental physicists, are here that are interested in new physics searches. No, I'm safe then. Interested in doing new physics searches. Okay, so I'm safe, and I can safely say that I think most of them went about this problem in a wrong way up until now, because most of the results on new physics searches, this is a table, I believe, from Atlas, but CMS and the other experiments are very similar tables. In most cases, research for new physics processes happened in a model-dependent way, meaning that we went to our friend theorists, asked for the most probable or the most interesting process that we want, model that we wanted to test, designed our selections and our detectors in order to optimize the sensitivity to that specific problem, and then we went and analyzed our data to look for it. And all of these bars tell you the range of energy that we have already excluded. So we looked, I don't know, for each one of those lines up to mass scales of the order of the TV, and we already know that there is no physics search that happens in that way. But is it really the most efficient way to deal with a problem like this? Now, if there are computer scientists here, they will say, obviously not. The most efficient way of doing this is anomaly detection. Okay, what does it mean? Anomaly detection means that if I have very precise knowledge of how the standard model works, if I know very well how the physics, I've done my homework, I know how electrons, protons, Higgs work, then anything else that behaves differently, it's an anomaly and it's a sign of new physics. Then I can target my algorithm to recognize very well how my known physics works, and then it would flag automatically anything else that looks different, okay? And this is something that it's much easier than trying to, and much more general, than trying to do a very specific model-dependent search. Because I can run this at trigger level, and then I can say, oh, I found an anomaly. What is this? This is an interesting event. I'm going to store it, and I'm going to further analyze it at that point, comparing it to all of the possible results that our friend theorists have produced. Okay, so we have defined, keeping this example in mind, a hybrid approach to this problem. And for a specific physics, I mean, for a, not specifics, but like for a relatively general physics signature, meaning a bunch of particle jets that are, so collimated sprays of particles that move along the same directions, a certain number of them. Those would be, for example, produced by Higgs, by the Higgs boson, a specific decay of the Higgs boson. In any case, it doesn't matter at this stage. But it's something that can happen. It's very common in the standard model, and can also appear for many different new physics searches. So what we did was to set up a classical algorithm for data compressions. I said quantum computers at the moment are not really good at analyzing large amounts of data. So what we did was, okay, we need to study something of the order of 300 variables per jet, and we want to study 2 jets. So we are talking about, as the input, we need to be able to analyze 600 variables every time we look at a collision. And this, with current quantum computers, it's impossible. So we compress it through an AI model. It's an autoencoder for those of you that are interested, which is a standard tool for doing lossless compression. And then we take this compressed representation of our physics data and we run it through our quantum algorithms. And here there are 2 kinds. The nice thing about those algorithms is that they are trained in a completely unsupervised way. Okay, we don't tell them what is new physics and what is old physics, standard physics. They learn it by themselves. Okay, what do I want to show you here? We don't need to go into the details. What this curve means, if you try and try to analyze and count how many times your model will give you the wrong give you the wrong answer, and how many times will give you the right answer in flagging new physics, then you can build curves like this. It means that if you are doing very, very good, you should have lines that cluster toward that corner. Okay, you want to have a very, very high rate of how often you get the right answer, and you want to have, this is the, just to make things simpler, sorry, this is the inverse of how many times you give the wrong answer. Okay, so when these curves cluster towards that corner, then your tool works nicely. And so we built quantum implementation of those and classical implementation of those. And we saw that in all of those different colors are colors that relate to the different possible new physics models. And in all cases, our quantum models actually work much better. You could say, I'll say it for you, that this is a log scale. So in fact, this difference is not so relevant. But actually, if you study this from the point of view again, not relevant in the details, but if you study it from the point of view of the amount of quantumness you introduce in your classifier and the size of your detector, and you choose specific realistic working point, meaning that, for example, you want to impose your tool to be able to be right at least 80% of the time, then we see what this curve shows you is that in all configurations, except maybe only one, the quantum models do much, much better. And it's the amount of quantumness in those tools that's actually driving the performance, okay? So this is not just a matter of how we are doing the training or the resources that are used or the amount of data that we use, but it's really intrinsic in the way we design the algorithm, okay? I have no time to go into the details, but please ask questions if you are interested. We can talk about this later. Another probably more friendly example is about beams optimization. This is some work that we did with our colleagues from the accelerator department, and they are studying the ways that can make more and more automatic the control systems for the accelerators, and in particular tuning of beams. If you can imagine, this is the distance along a linear accelerator and also have deflection angles of your particle beams, then you can tune your magnet in such a way that those beams actually collimate, go straight, basically, and reach your target at the end of the accelerators, okay? That's a simplification, but this is a real beam line that exists at CERN to accelerate electrons towards a specific experiment, okay? It's called the awake beam line. And it's made out of 10 positions in which you can tune the beams through your magnets, and you can measure their distance from the optimal ones, okay? So 10 monitoring stations and 10 tuning stations, okay? So this is the problem we decided to address. It's an optimization problem. And we did that setting up a hybrid algorithm again, in which this is AI-based, so quantum AI actually. If you want to be precise, this is quantum reinforcement learning algorithm. What we found, the only thing that's really, really important, in fact, you should look at both plots. This one compares the quantum algorithms, which is in blue, to the classical one, and it tells you in how many steps the quantum algorithms reached the optimal behavior, which is order of 10 steps with respect to 400s that are needed in the classical case. And this will tell you how much data you actually need. This is still our quantum algorithm compared to a range of classical ones. And this is in log scale, the amount of data that is needed to actually do this training. Okay, oh, sorry, no, this is still the training steps, but it correlates in any case, because those are all experiments. So this looks like a small result, but it isn't at all a small result, in the sense that there are many cases in which the access to training data is a problem. And for the accelerator people, it's really the case, because every time they need to collect training data for this kind of experiments, they cannot run for physics. Okay, so this is one of the cases in which already today the quantum computer actually makes a big difference. And what's really nice about this is the fact that we use the quantum computer to train and to optimize an agent, so the optimization agent, the control agent, that it's classical. So this agent can actually run at in the control room today. We don't need to have the quantum computer there, okay, which would be trickier. So those were examples, but basically this kind of work ended up into a white paper that we wrote at the end of the first 3 years of QTI2, together with Daisy IBM colleagues from Daisy IBM, that try to really evaluate, or at least list all the possible fields and applications in high energy physics where quantum computers could have an impact, okay? And it's available on the archive at the moment. And I forgot to put. I will upload this with the link to the publication. But what you will find in a white paper like that is this kind of information. Theoretical or theory-related use cases, experiments-related use cases. So this is mostly data processing, and this is mostly simulations of different phenomena. And so what we tried to do was to do an exercise of taking our problems, trying to classify them according to some specific, task description, and then trying to map them to the possible algorithms that exist already today in some form. Okay, not necessarily the most optimized one. And the same for the case of the experimental data processing. So anything that has to do, for example, with jet reconstruction or track reconstruction is actually can be configured actually as a regression or a cluster, right? Or a clustering problem, as in the case of musician. And that would be a set of algorithms that you could try to use to solve those. Okay, so I think this was a very nice results that we managed to gather from phase 1 of QTI. So now, as far as so this was really background work, okay? Exploration. What is it that we can do? I gave you a few examples. There is much more, but it really made us feel comfortable in the sense that this is a field that it's worth exploring. In all, I showed you 2 examples in which we see some advantage in using a quantum algorithm, okay? And we can discuss. I'm leaving this some advantage as a very vague definition to encourage questions later on. But in any case, this really tried to push towards new, more focalized studies. Okay, so if we go back to this initial slide, phase 2 is really trying to look more into this aspect. Okay, what is it? What are the particle energy physics that we can use to improve QT? I give you some examples. So this is a slightly different discussion that starts now, but I will still have another, I couldn't avoid it, another last QML slide at the end of this talk. So there are many kinds of things that we do at CERN that could be used to improve quantum technologies. There is a lot of work and a lot of experience that we have in designing control systems, data acquisition systems, data monitoring systems, optimizing, for example, artificial intelligence on ASICs and FPGAs in particular. This is a very important step for, the triggering issue that data acquisition step, efficient data acquisition step that I mentioned at the beginning. And this is expertise that can be reused as a readout. Not right away, so be careful. This is not a direct translation. Requirements in terms of latencies and accuracy of the results are very different. So this is not a free lunch, but it's an area in which the impact can exist. The possibility for impact exists. Another one is still related to, it's again related to accelerators technologies, and in particular CERN as one state-of-the-art facility for what concerns coatings for superconducting cavities. And this is a little bit about how hardware is built. I said CERN is not interested in building quantum computers, but we can help many different hardware technologies that are related to this. And this is one, because you can use RF cavities to do to build bosonic quantum computers. What does it mean? That instead of building digital computers, you can actually have build analog computers the way we used to work at the very beginning of the informatics era, which can have very interesting behavior. Those kind of computers in an analog mode basically work as simulators. So you set up a quantum state and you let it evolve the same way you would generate, for example, a collision in a collider. So that's really nice. But also RF cavities can be used within the readout chain of quantum computers. Okay, in particular as transducers to change to adapt the photons that are used, that are readout. Another example of a technology that we have today at CERN, and that again was developed for the accelerator infrastructure, is called White Rabbit. So at the moment, the LHC is what, 27 kilometers? It's 27 kilometers long. It means that you need to be able to ensure accurate time distributions. All of its parts need to be synchronized, okay? So years ago, this was already more than 10 years ago, the White Rabbit project had started. This is a and ensure, you can see it here, the very high synchronization precision and accuracy over a time scale, a distance scale of tens of kilometers, okay? Because this is the size of what we have at CERN and what we need. Now, it turns out that this technology can actually scale out. In fact, the White Rabbit collaboration was just launched at a much broader, at the European level. There are open discussions, a very active discussion with the GÉANT network in order to and the other metrology and the metrology institutes in the different countries in order to test the White Rabbit protocols within the general time and frequency distribution networks at the European level, okay? Why is this relevant? Also, this is all classical technology. Why is it relevant for us and the QTI? It's important because this is an important ingredient if you want to do quantum key distribution, for example, or if you want to work towards quantum internet. So the sharing, doing distributed quantum information. So keeping these kind of examples in mind, we built QTI phase 2. Now this is really organized in 4 main areas. One is about computing and algorithms, and before there is this part about networks and communication that is stronger, because we are really now looking into what are the ingredients that are needed to build infrastructure, for example, for QKD, not just trying to use it. Quantum technology part that's looking into hardware for sensors for detectors. And of course, we decided to dedicate a full work package, a center of competence to the collaboration for impact. It gives you an idea how important that is for us. And now we come to one of my favorite slides. I'm sorry, I am very biased. I worked on artificial intelligence for many, many years, and so I naturally moved this into the quantum domain. This paper came out February, but not so recent anymore. Researchers need to work a little harder for the next nice paper. So why do I show it here? Because it's a paper in which we really try to put together a lot of different contributions and a lot of different technologies, okay? What is it about? So from the technological perspective, we are interested in 2 main parts. One is to which extent we can use tools, tensor networks in particular, are one such classical tools in order to simulate quantum systems, and up to which level basically we can do that, and when does it become not possible or too difficult anymore, so suboptimal. And how does this interface with a quantum solution, and to which extent we can imagine that using a quantum algorithm on quantum data could actually be advantageous. Okay, so those are the 2 main questions: quantum systems and quantum algorithms for quantum data. How do they work together? So what did we do? We choose a specific physics model. This is a physics model that it's called the any model. There's no typo there. That's actually 3 N's. Next nearest neighbor, the NNN means next nearest neighbor interaction. So this model is a model that describes the interaction of a set of spins. I'm almost there. Spins. And basically, it's an interesting model because many processes, but in particular, if you try to draw its phase diagram, so the phases in which a system of spins like this would appear in the real world, you would have a phase diagrams that is actually quite rich. So, for example, for the case in which all of your spins in the system could be all aligned in one direction, you would call that the ferromagnetic phase. Talking about ferromagnetic, paramagnetic, maybe this kind of language resonates from physics 2 courses in high school. No, maybe. But okay, this is what I'm talking about, the different phases that are related to the different relative configurations of the spins. So you can use tensor networks to actually simulate how to generate this diagram, okay, how those systems behave. And typically, you have a certain number of parameters that you can tune, and this diagram is with respect to these parameters, okay? So the first part of this work consisted in using a tensor network to generate those states. And I don't know how familiar you are with tensor network, but I can tell you that we managed to simulate a state that had as many as 460 spins, which is very, very high, because I believe that up until now, most of the state of the art is in the orders of tens, okay, below 100, at least for such detailed description. It was a collaboration between my group and theorists. If you look at the paper, you will clearly see that there is a section that goes into the details of the characterization of these faces. Okay, so if you're interested, you can really, really amuse yourself in looking into the number of properties that you can actually characterize with tensor network. Okay, then now we have this nice way of describing the states. What do we do with them? We load them on qubits. We build the quantum states out of that. There are specific tools that can allow you to do that, and still you can recognize how the different phases in the space diagrams are. And once we have a system of qubits that represents the different points on this phase space, then we can tune or train our quantum machine learning algorithm to actually recognize, to tell me when a point in this part of the space belongs to a specific phase that is different than that, and that is different than that. I want to stress right away your attention to this line. This is called the floating space. It's very difficult to see, to reproduce, and to characterize, okay? What we find is that, okay, this is the input to our system. Forget about it. This is a way of preparing a quantum state that represents a different point in that specific phase diagram. All of this is a way you would build a convolutional neural network, for example, in the quantum domain. Okay, so doesn't matter the details. What's important is that this is a network that you can train in a supervised way. Remember the discussion I made at the beginning about model dependence and model independent search. This is a tool for model dependence. I show a state to the network when I train it, and I tell it this is a ferromagnetic phase. I show another one, I say this is a paramagnetic phase, okay? And if I do that for 12, 16, or 20 qubits, then I see that the network can actually recognize more or less the shape of the diagram, okay? You can also see that it doesn't really recognize everything. In particular, unless I explicitly include points from this phase in the training set, then the network doesn't know anything about it. Here, there are no points from that floating phase, and you see that the network obviously cannot make them up. This is model-dependent, supervised training. And it needs to see at least some of them in order to recognize it. Now, look what happens here. This is the very same problem in which I change my QML architecture. I train it in a completely unsupervised way, meaning that I just take a point at the origin of my phase diagram, okay, that contains the physics in the most simplified fashion, and then I run my autoencoder, my unsupervised network, basically to tell me how different from here, so basically how far away from here my physics points are. And amazingly, you see that the network, the boundaries, so the phase transitions are a little less defined, but the network more or less gets the right structure. And in particular, if I increase the number of qubits, so the complexity of the system, my completely unsupervised model starts to recognize that there is a floating phase here. This is an amazing result. It tells us that we are able to basically see the unknown, to recognize there is something there, okay? So, yes, thanks. I got carried away. Last thing I want to say before the conclusion, I talked about computing. Again, that's what's closer to the heart, but I shouldn't focus on that only. So I take the last slide to stress the fact that there is actually a lot of work that is ongoing on sensing too. In particular, CERN is very committed and very much involved in the ECFA that defines a strategy for future detectors for future colliders. And within the ECFA strategy roadmap, there is a particular part that is dedicated to studying quantum sensors for detectors. And so there is a new proposal for a collaboration, the DRD5, well, in ECFA jargon, that is being set up, that actually covers a huge amount of topics within the field of quantum sensing. Okay, I'm mentioning this here because if there is interest in this community to actually participate, to work and involve on quantum sensors, this would really be a good way to enter. And there are a lot of topics that are covered, from basic technology. So we are talking about real development of new core solutions for new materials, to, for example, already, where is it? Well, I didn't write it explicitly, but for example, to the point of building distributed network of sensors that at the European level, so at the transnational level, could be used to build networks of how do you say, of coherent detectors, okay, for future searches. And I mean, I'd rather you ask questions than me going through the outlook again. So please, thank you for your attention.
Yeah, I think this was also a hiring keynote speech, and thank you for all of this information, which I can imagine many of us, even including me, didn't recognize so far. So maybe we have 2-3 minutes. So if you have some imminent past question, yes, Gergely, but wait a minute, wait a minute. If no, not yet. Ah, yes, please. Will not be forgotten.
A few years ago, we said that there were no quantum computers and quantum algorithms, the classical ones. But you said in this speech that has it changed in the last 1-2 years?
So there's two forces that are coming together. One is the fact that we are changing the definition of what we consider advantage. All of the work and theoretical initial steps toward building quantum algorithms was coming from mathematicians and complexity theory. So we were really trying to find algorithms that would be proven to scale in a much better way than classical. Okay, you have a problem that classically scales to solve it at some point. You can think it becomes logarithmic, polynomial, logarithmic. So if you can get a scaling using a quantum computer that is better, then that is considered the advantage, okay? Now, that is still true, and it's still relevant, in particular for the search of new algorithms, but we live in a way, in an era of practical applications. So if we need to also extend the concept to, for example, cases in which it could just simply be to use a quantum computer for a few fractions of a second rather than use an HPC center for, a classical, because actually quantum computers are integrated in HPC centers, but it's another discussion. But let's say purely classical resources for minutes, okay? So this is one way of seeing this. And also I showed examples of cases in which, for example, you don't have access to a lot of data. Or you have other kinds of constraints. So if you put all of this together, then you start to find areas in which it could be beneficial to have a quantum computer.
So in short, can you say that it is more beneficial now?
Yes, okay. Sorry, yes. In short, I would say that yes. Now, please take into account that there are purists that wouldn't agree with me. Okay, that I would say, unless I have an algorithm that I know that scales better in the quantum domain than in the classical domain, it's not worth it. But for me, this is too restrictive.
Okay, thank you.
Thank you so much. Gergely?
Yeah, okay. So thank you very much. It was a beautiful overview of the past and future. I would have two questions. One is a rather technical one related to the White Rabbit protocol and the exit switches, which I think this could be a good opportunity for institute like us to join somehow. So Could you please tell me a little bit more about the technology? So you mentioned that the white rabbit switch itself, it's available, you can get it, but required to have a special network, or you can use the standard one.
So this works also on Ethernet.
I purge my personal white rabbit switch, and then we can just plug it to the giant, and I can reach.
Yes, because in the nodes there is this continuous monitoring and recalibration of the signals that happens continually in a way that is completely distributed, and that's actually the way it manages to scale. Now, if you want this, that's fine. It can run on very easy network. Of course, if you want to go to certain levels of synchronization, for example, to dedicated network, to fibers,
but then
that's different.
Fibers should be also the special ones, or just the standard one but dedicated?
It depends. Again, you can use them. It depends on your application. For example, if you want to apply this in the very high precision time or the frequency domain, then you would have dedicated channels. Then it's really very much about the protocol that is used for the distributions of this. I mean, because I'm not an expert, but I know that this can happen in different ways. You can decide channels in which the different signals overlap, or you can decide to use dedicated channels. But whatever you use in that domain, then you can adapt your white rabbit to actually work in that way.
Okay, but it's still do not need to put new cables.
No. In principle, no, not at all.
No,
No.
Yeah, I have the second.
The infrastructure that you need are the switches and the nodes, but it can work on the network that you have.
Okay. The other question is rather theoretical. Can you go back to something like 16 or 17, what you had, where you had this, how we should, this one, yeah, the anomaly detection. And I mean, this is how physics works. This is the reality, how reality works, that there are a human being in the beginning who is a quantum object, practically. And there's a human being at the end of the day who is a quantum object. And I mean, what I have experienced from theoretical physics, typically it's very hard to put if you have an anomaly and if you have a standard way in a new method. And the question is with these quantum systems, where there are even more things which we do not really understand on the different processes, how can you trust the people on the other side, the same quantum systems on the other side, for this kind of algorithms? Because even the standard, mathematical, analytical calculations with the new technology is very hard to push through on the system.
Yes, so this is true so this is a problem that is not specific to quantum. Okay, so this is our community is very, very conservative. Okay, so high energy physics and AI actually are starting to talk to each other relatively recently because of this, and the fact that you get to a point in which there is the usual black box discussion that happens. Now, it actually turns out that when you start to using these tools, and works in the exact same way for quantum computing, okay, in the two cases, they're just two different kinds of boxes, but you can train them, you can, while you develop them for your applications, you can learn how they work, and you can characterize how they work. You can validate the results, and you can correlate, for example, the results that you obtain to the choices that you make at the beginning, at the level of the input. So when you provide a tool or you explain how something works, you also show all of the evidence that covers these different topics. The systematic studies would be in our domain, right? This is what physicists call them. But all of the systematic studies in the general world are called explainability of AI. It's the same thing. So if you do that, then it's much easier to convince the quantum scientists that is here that this is
But I think this problem will be solved by the quantum press office. If there is no new news after 2 months, they will say that, okay, show us something extraordinary. I don't care how did you get it. We want to communicate it. So, and that will help Gergely to break this barrier to accept the new results.
Yeah, I think it takes patience to break the barriers. You need to prove that you are robust, and you can do it, right?
And reproducible.
Yes, and reproducible.
Okay, so thank you very much, Sofia. We really appreciate your time and energy and that you are with us. So I think now let us have a little break to refresh yourself. And let us thank both Sofia, and unfortunately Roland Jakob needed to leave for another meeting. So let us thank for all of you, the keynote speakers. As a little break, and Gergely will be the next chairman, and use the opportunity also to ask Sofia, because I think you must leave in the evening, so which means that so tomorrow you will not be here. Thank you so much. Okay.